Good afternoon, ladies and gentlemen. It's my special pleasure to present to you my work on the design of an embedded 2D imager of Microscale Flowmetry based on Optical Feedback Interferometry. I'm a member of LAS CNRS from Toulouse, France. So in the microfluidic field of research, we have two main domains of applications. In the chemical one, we have the design of microreactors. In the biomedical one, we have the need of measurements in microcirculation and blood perfusion. All of them request a high resolution velocity measurement. The actual technologies, both based on imaging methods and Doppler ones, are high cost, bulky, and complex. So considering the context, we saw the opportunity for an innovative 2D imager, integrating the features of compactness, cost-reduced instrumentation, and high resolution. So we propose a 2D imager based in optical feedback interferometry with MEMS mirror. On OFI Sensing, the sensor itself, it's a laser diode. It's compact, low cost, and simple. The principle of optical feedback interferometry can be described by this picture. Once you have the light emission of the laser reaching a target, part of the light is backscattered and re-entering the laser cavity, so interfering with the laser itself. So changes on the external cavity produce laser power modulation. The main sense applications with this technology are for displacement measurement, sound characterization, and velocimetry flowmetry. On optical feedback velocimetry, the particle that cross the sensing volume of the laser scatters the light, and we have a contribution of each particle. So across the velocity distribution, we have a distribution of frequency according to the Doppler equation as shown here. So on the constitution of the OFI signal, we have the sum of contributions of each particle scattering the light, so modulating the power of the laser. So as you can see, we have a distribution of frequency related with the distribution of velocity of the sensor itself in the spectrum of the signal. So we have here the power spectrum of the OFI signal at several flow rates. So once we increase the flow rate, we have an increasing of the amplitude across the spectrum of the signal. The average velocity can be exploited by the average Doppler frequency that through the statistical approach of the first weighted moment, as described by this equation, we can have such measurement. In the system architecture, we have the optical part is constituted by the collimate lens, the focusing lens, the laser itself with the photo detector packaged in the same component. So as you can see here in this picture, so the photo detector it's back in the back mirror of the laser cavity. So we have the electronics itself, and in the electronics we acquire the OFI signal through the current of the photo detector. We pass it through a transimpedance amplifier. We pass after through a bandpass filter to improve the signal modulator. And all this data is acquired by the data acquisition card and the signal processing in a computer. Regarding the scanning setup, we have here the laser diode itself. We have the collimate lens. To create the 2D scan feature, we use a XY MEMS mirror. so you can scan in both directions. We have a focal lens to focus the laser beam into the target, and we used a microscale support to impose the Doppler, to impose two angles to create the Doppler effect, as you can see in this picture. The maximum area of scanning is 20 by 20 millimeter, and the maximum spatial resolution is 5 micrometer. So the dotted red line indicates the laser centered into the mirror, and the black ones, as you can see here, and the black ones indicates the extreme of possible scanning in X. So the same for Y. Here you can see a picture of the first prototype. So it's the 3D drawing used for the first prototype of the system. Regarding the results, we started by the line scanning. So for that, we set just the angle theta 2 is different from 0, so we can create a 1D Doppler effect. So we put the channel vertically, and we set the scanning like that. There, just one line. So the channel itself is a transparent plastic circular tube of 500 micrometers of inner diameter. The target fluid is a full milk pumped at constant flow rate. So as you can see in the results, we have here the average Doppler frequency across each position of the diameter of the microchannel. So according to the fitting curve, we can see that our measurement is validated. Our measurement is validated respecting the Cauchy law. The scanning resolution is around 80 micrometers. So we pass now for 2D scanning to create a 2D image. So in this case, we use a microchannel with serpentines, and we set the support now with two angles. So changing the theta 1 from 0 to 3. So in that way, you can create the Doppler effect in 2 dimensions. The microchannel has a SU weight photoresist of 100 by 100 micrometer, and the target fluid is full milk pumped at constant flow rate. The image area chosen, it's this one indicated, so we can scan the smallest separation between the serpentines. So in that way, you can also validate the resolution of scanning, as the minimal separation is 10 micrometer. So this is the result. We have here a picture of 50,000 pixels, 300 by 50. And as we can see here, the resolution is 5.8 micrometer. And we can even hopefully validate the width of the microchannel. As we can see here, the measurement is around 116 micrometer. Regarding the scanning time, we have some main factors affecting the scan time is the number of samples by pixel. Considering the 5,000 pixels at this amount of samples, we did that image with around 185 minutes. So we saw that it's a point to do prospections that require improvement. In that way, I consider a new image changing the number of samples by pixel. So I divide by 4. So we reached 46 minutes, and divide by 20, we reach around 5 minutes. What we can see about the image itself is that we have a decreasing of the smoothness of average velocity across the channel. But we can still detect the channel itself. So this is information that is useful to be considered according to the application that we desire to use our sensor. As a conclusion, we validate the innovating of E2D imager using a beam-steering MEMS mirror. That MEMS mirror enable extremely compact, potentially handheld device. Because before the team used a scanning, a mechanical mounting to scan in 2 dimensions. So it's called a technology with an instrument called Zeba. So it's a huge setup and mostly operating optical table. We could reach and validate, according to our motivation, a high spatial resolution, so reaching 5 micrometer. As perspective for the future, we see the need of improvement of signal processing, as according to the application to handling the device, we needed to enhance the robustness of the signal processing according to the mechanical perturbations on the system. We should also consider the exploration once we have the signal. So we should explore the application of non-invasive biomedical applications. So as we can use for application of, for example, measuring the blood perfusion under the human skin in vivo. As we have nowadays several applications on such field like that. We should also explore after that the velocity profile of droplets interface inter-microreactors, so attending the domain of application of chemical field. Thank you so much for your attention. I'm available for questions.